Yes, good morning, all of you. We are discussing about the sp3d2 hybridization. See, what is the meaning of sp3d2 hybridization? Is nothing but one s orbital and how many 3p orbitals and how many 2d orbitals are intermixed together. Means how many 1s, 3p and 2d together. 6 orbitals are intermixed together. Then we are getting which hybridization? sp3d2 hybridization we are getting. We are getting how many hybrid orbitals together? We are getting 6 hybrid orbitals we are getting. How many atomic orbitals are intermixed? The same number of hybrid orbitals we are getting. Then geometry is octahedral geometry. This octahedral geometry is also calling as square bipyramidal shape. Square bipyramidal shape. And what angle we are getting? Nothing but is equals to 90 degrees angle we are getting. So what is the meaning of sp3d2 hybridization? It's a board examination point of view, either sp3d or sp3d2 is a guarantee question. See, one s orbital and 3p orbitals and 2d orbitals are intermixed together. We are getting 6 hybrid orbitals. The geometry is octahedral geometry, or also called as square bipyramidal, and angle is 90 degrees. Sir, how is this 6 hybrid orbital will be arranged? They should not be kept side by side. Why? Because when you place them side by side, repulsion will be high, stability will be less. So what is the concept of chemistry? Always should get the stable structures. How it is that one I will show you, see carefully. Yes sir, out of 6 hybrid orbital, 4 are coming in the same plane like a square, and above one hybrid orbital is coming, below one hybrid orbital is coming. So then you can join these vertices of these hybrid orbital are nothing but bonds. We are getting square, and after that above bond is coming, no, that will be joined as 4 corners. We are getting pyramid, and like that we are getting below also pyramid we are getting. Yes or no? So that's only we are calling as square bipyramidal. Example for this is nothing but SF6 molecules. So what is the meaning of SF6? How many fluorines were there? Hexa 6. Hexa fluoro sulfur. Or sulfur hexafluoride, you can write it like that also, is not a problem. Sulfur hexafluoride. Hexafluoride is the SF6. And what you have to discuss here, in sp3d2 hybridization, what is the percentage of s character? S character percentage means number of s orbital 1 by total hybrid orbital 6 into 100. Do you know how much you are getting? 1, and we are getting 16.66 percentage we are getting. What is the percentage of p character? Is nothing but how many p orbitals is intermixed? 3p orbitals into 100. You are getting around 3 6 are 18, and 3 6 are 18 and 19, 3 6 are 18 and 19, and 49.98 percentage we are getting. And what is the percentage of d character in hybrid orbital? Because mixed knows compulsory some character will be there or some percentage character will be there. How many you are getting? 1 by 6 into 100. We are getting 16.66 percentage we are getting. Together we are getting how much? Sorry, 2 by 2 of d orbital by total hybrid orbital 6 into 100 is nothing but 2 times 2 12s 2 6 12 and 3, and we are getting 12 plus 2 1s 3 is nothing but 40. Means together we are getting 100%. Now we have to discuss about the in SF6 molecule how we are getting that sp3d2 hybridization. Sulfur atomic number 16, configuration neon, and 3s2 and 3p4 and 3d0. Generally valence shell orbitals will be involved in the hybridization. That only I am showing here. 3s orbital and 3p orbital and 3d orbital. 3s is one type having how many electrons? 2 electrons. 3p are of how many types? three types. Having how many electrons? 4 electrons. First one goes into each orbital, then only pairing is happening. Right now d orbital will be vacant. How many are there? 5 are there. This is which one? Ground state electronic configuration. Now you supplied some energy, then it is going into first excited state electronic configuration. First excited state means electron has to be jumps from one shell to another shell or one orbital to another orbital. First of all, 3p to 3d. Why? Because they are side by side, means energy gap is less. So that's why first of all electron jumps from here to here. After that 3s has a pair of electron and 3p has only 3 electrons like this, and 3d has one more electron will be there like this. Yes or no? Now still it will be participating in the one more excitation by absorbing energy, that's calling as second excited state electronic configuration. While supplying still more energy, actually gap is more. Even though you are supplying more energy, no, that's why electron can also jump from here to here. So then what we are getting? S orbital has single electron, p orbital also has single electrons, yes, like this, and 2d orbitals also has electrons. Okay, now what happening? Hybridization is happening. One s orbital and 3 p orbitals and 2 d orbitals are involving in the sp3d2 hybridization. We are getting 6 hybrid orbital we are getting. Now come to the concept, means how to write down. In SF6 molecule sulfur is involving in the hybridization in second excited state, then we are getting 6 hybrid orbital we are getting. Check it carefully. Sulfur around it we are getting 6 hybrid orbital we are getting. Out of 6, 4 are like a square shape, one is coming like room. Imagine at the center sulfur is there, for 4 corners 4 hybrid orbital, one is coming above the plane, another one is coming below the plane. Now what happening? Sulfur is involving in the bond formation with fluorine. Yes, what is the fluorine? Atomic number 9. Configuration 1s2, 2s2 and 2p5. You know very well, according to BBT, valence shell orbitals is involving in the overlapping process. That too, 2s has 2 electrons, is a pair. It's not involving in the overlapping process. 2p are of how many types among? 3 types. First one electron goes into each orbital, then only pairing is taking place. Yes or no? Yes. These are also present in the valence shell but not involving in the overlapping because it's a pair. According to BBT, valence shell orbital with single electron participating in the hybridization overlapping process. That's what this is. What is that orbital? 2pz orbital. Yes, this is the sp3d2 hybrid orbitals, or this is involving in the overlapping with the 2pz orbital of the fluorine atom. So they are involving in the hand-on overlapping, give sigma bond because they are approached together through its internuclear axis. Same situation this side also, fluorine is coming with 2pz orbital through its internuclear axis, and on overlapping give sigma bond. Like that here also fluorine is coming with internuclear axis overlapping and gives sigma bond. Here also fluorine is coming like this through its internuclear axis, we are getting sigma bond. After that sulfur has 4 bonds with fluorine atoms. Okay, like this. Then what shape you are getting? Square shape you are getting. If you can show like dotted lines here, which shape you are getting? Square shape you are getting. But still we have 2 more hybrid orbital. One is above the plane, another one is below the plane. There are also which orbital? sp3d2 hybrid orbital only. Okay, they are also having single electron and they are also involving in the overlapping with pz orbital of the fluorine through its internuclear axis. We are getting one more sigma. Here also we are getting one more sigma bond because through its overlapping is going on. So finally, above the plane you are getting one fluorine bond and below the plane you are getting one more fluorine bond. So that's why the SFFF 4Fs are like a square, and above one fluorine, below one fluorine, above one pyramid, below one pyramid. If you can join these vertices, we are getting pyramid. Above pyramid, below pyramid, calling as bipyramidal, and square shape. This is calling as square bipyramidal, also called as octahedral geometry. So that's calling as SF6 molecule. And now angle. So what angle we are getting? Totally angle is how much? 360. 360 divided by how many parts? 4 parts. So this part we are getting angle here is nothing but 90 degrees. And axial bonds is also making angle is how much here also? 90 degrees. This part in SF6 molecule we have only one type of the bond angle is nothing but 90 degrees will be there. All of you understood? Yes. Now we are going to next type of hybridization is nothing but sp3d3 hybridization. Yes, you will get it. I think by seeing that only we can define the definition. What is that one? 1 s orbital plus 3 p orbitals plus 3 d orbitals. 3 d orbitals. 1 s orbital, 3 p orbital and 3 d orbitals which are having similar energy or intermixed together, we are getting 7 hybrid orbital we are getting. Why? Because how many are intermixed? 7 are intermixed, that's why we are getting 7 hybrid orbital we are getting. The phenomena is calling as sp3d3 hybridization. So intermixing of 1 s orbital, 3 p orbitals and 3 d orbitals together, we are getting 7 hybrid orbital, all are having same energy and same shape. The phenomena is calling as sp3d3 hybridization. The shape is nothing but pentagonal bipyramidal. Pentagonal bipyramidal in shape. Sir, how is that one and what are the bond angles? The bond angles are of two types here. One bond angle is 72 degrees, another bond angle is 90 degrees. I will explain that one. So together we have how many hybrid orbitals? 7 are there. How they are arranging? The 7 are not like side by side. Why? Because if you take side by side, repulsion will be high, stability will be less. That's why. Out of 7, 5 are appears like a tortoise. How tortoise will be there? 4 legs and 1 head will be there. Like so, 5 hybrid orbitals are arranged in the same plane. So I am showing that only, you see carefully like this. Out of 7, 4 or 5 are lying in the same plane. So if you can join these vertices, what we are getting among? Pentagonal shape you are getting, pentagonal ring. It is similar to like this. How many edges are coming? 5 edges, this is calling as pentagonal. And still we have 1 hybrid orbital above, 1 hybrid orbital below. That's why is calling as above 1 pyramid, below 1 pyramid. That's why is calling as pentagonal bipyramidal in shape. Now I want to show it very clearly. So hybrid orbital forms which bond? Sigma bond, like this. So all will be like a pentagonal ring, and after that above 1 bond is coming, below 1 bond is coming. So whatever 5 bonds which are lying in the same plane, so total angle around the point is 360 by 5. Nothing but 72 degrees is coming here. And whatever above bond and below bond is there, their making angle is how much amount? 90 degrees will be there. That's why in pentagonal bipyramidal we have 2 bond angles 72 degrees and 90 degrees. What are the example for this molecule or IF7? IF7 example. What is the name of this one? Heptafluoroiodine. Iodoheptafluoride. You can write it like that, no problem. And in sp3d3 hybrid orbital, what is the percentage of S character amount? How can you find out the percentage of orbital character? Number of that particular orbital by total hybrid orbital into 100. In this process, how many S orbital? 1. By total hybrid orbital is 7 into 100. Is nothing but 1, and here we are getting 730, no, is nothing but 14. 14.2 percentage. And what is the percentage of P character amount? Is nothing but 3 by 7 into 100. Is nothing but 6. 3 4s are 12 and 3 4 3 plus 1 42.6. And what is the percentage of D character amount? Is also same thing, 3 p orbitals, d orbitals by total hybrid orbital into 100 is nothing but 42.6. So together we are getting 84 plus 14 is nothing but around 98, as well around 100% we are getting. Are you getting or no? Yes, this is the percentage. Now we have to explain about the IF7 molecule. See, in IF7 molecule, what is the central atom that will involving in the hybridization? Iodine is the central atom, atomic number 53. So if you want to write on the configuration, it is nothing but krypton 4d10 and 5s2 and 5p5. So count it, krypton is the 36 plus 10, 46 plus 7, 53. So now in every atom generally which orbitals are involving in the hybridization? A last shell or valence shell orbitals is involving in the hybridization. So write down that one clearly, 5s, 5p and 5d. Okay, now write down ground state electronic configuration. 5s having how many electrons? 2 electrons. Can be shown them as a pair? Yes. 5p are how many types? 3 types. Having how many electrons? 5 electrons. How to fill them? First one goes into each orbital, then only they are involving in the pair. Right now, is there any electrons in the d orbital? No. That's why vacant. Now, you are supplying energy to this one. Listen carefully. This is nothing but the first excited state electronic configuration. Electron will jump from here to here or here to here. First side by side, because 5p and 5d having less energy gap, that's why immediately jumping. So happens like this here. Then no disturbance in the 5s as usual. In 5p, out of this one already one paired as usual, one is becoming unpaired. That electron goes into which orbital? D orbital. Yes or no? Yes. See, the process cannot be stopped. Still you are supplying energy. Then it is going into second excited state electronic configuration. Electron jumps from where to where again, from here to here. Then we have S with 2 electrons and P has 3 electrons. S like this, and D has 2 electrons. Are you getting or no? Yes. Still, it has to be supplied energy. Then the atom or space goes to third excited state electronic configuration. Means electron jumps from here to here. So then what we are getting? Here we are getting a pair, means a single electron. 3p orbitals is also has single electrons, and 2d orbitals is also has single electrons. 3d orbitals also has a single electron. Now in IF7, iodine heptafluoride, the central iodine atom is involving in the hybridization in third excited state. What is the hybridization? sp3d3 hybridization. Under sp3d3 hybridization, we are getting how many hybrid orbitals? 7. All are involving in the sigma bond. I will show that. Iodine. So around iodine, we are getting how many hybrid orbitals? 7. Out of 7, 5 are like a tortoise. So 4 legs and 1 head. So these all are nothing but which orbital? sp3d3. They all are having single electrons. Already we seen previously. Iodine is involving in the bond formation with fluorine. The fluorine is involving in the overlapping with which orbital? 2pz orbital. That's why each fluorine is coming with the 2pz orbital. Through its internuclear axis will form sigma. Like that, 5 fluorines is approaching to its internuclear axis, we are getting sigma. Again here also we are getting fluorine with 2pz orbital, sigma. Here also we are getting 2pz orbital, we are getting sigma. Here also we are getting fluorine with 2pz orbital to its internuclear axis, we are getting sigma. So right now, what shape you got? Iodine center, 5 bonds like a pentagonal ring we got. So every corner is nothing but fluorine atom will be there. Are you getting on? Yes. Now making angle is how much? 72 degrees will be there. Why? Because total angle 360 divided by 5 parts. And above one hybrid orbital is coming, below one hybrid orbital is coming. They are also overlapped with fluorine atom of the 2pz orbital through its internuclear axis sigma. Same situation from down also, fluorine is approaching with its internuclear axis, we are getting sigma. That's why again above we are getting 1 bond, below we are getting 1 bond. So here axial bonds are making angle is how much? 90 degrees. These above bond and below bond is one category, remaining all are another category. My question, out of axial bonds and equatorial bonds, which is the stable bonds? axial bonds. Why? Because making angle is 90, more angle, less repulsion. Less repulsion, more stable. But if you take equatorial bonds, making angle 72. 72 means bonds are close. Bonds are close, repulsion will be high. Repulsion is high, stability is less. Did you got my point? Yes, this is the information regarding all types. But sir, in competitive, how can you do? Just I will tell you one formula how to do the competitive things. It's a very important formula. See carefully. See, I will tell the formula for hybridization. The very important, all of you write down somewhere for hybridization formula. So write down here, appearance may long, but while applying you can get very easy. Number of hybrid orbitals. Number of hybrid orbitals is equals to number of atoms around the central atom, by seeing few examples you will get it, plus half into group number of the central atom minus number of bonds around the central atom, plus or minus charge. So what is the formula? Number of hybrid orbital is equals to number of atoms around the central atom plus half into group number of the central atom minus number of bonds around the central atom plus or minus charge. I will tell you something. So first example I am telling, I am taking for example H2O, I am taking H2O. So what hybridization is taking this I want to come to. So in H2O what is the central atom? Oxygen is the central atom. Okay, write down here. Number of hybrid orbital is equals to number of atoms around the central atom. Around the oxygen how many atoms will be there? 2 atoms is there, 2 hydrogen atom plus half into group number of the oxygen. Group number of the oxygen is 6A group element, means 6 minus. Okay, now around the central atom bonds, every hydrogen can form one bond, like that 2 hydrogen can form 2 bonds. Okay, is there any charge? No, that's why leave it. Now do it one thing here. So we are getting 2 plus 6 minus 2, 4 by 2. So is nothing but 2 we are getting. So we want 4 hybrid orbital, we want 2 plus 2, 4 hybrid orbital. Yes or no? So 4 hybrid orbital is possible in which hybridization? sp3 hybridization. Yes, very important thing. In this formula, always first number gives number of bond pairs and second number gives number of lone pairs. Yes, very clear. In H2O molecule, yes, what is the shape? O and H like this. 2 bonds are there and 2 lone pairs were there. 2 bond pairs, 2 lone pairs. Okay, I will give you one more molecule. Check it for example. CO2 is there. So what is the hybridization, sir? Number of hybrid orbital is equals to, what is the central atom here? Carbon is the central atom. So right, number of atoms around the central atom, how many? 2 atoms plus half into group number of the carbon, 4th group element, carbon, silicon, germanium, 4th group element minus. Each oxygen can form valency of oxygen 2. How many are there? 2. 2 2s are 4. Yes. Now we can take it. So 4 minus 4, 0 by anything 0 means you are getting 2 plus 0. We want 2 hybrid orbital. 2 hybrid orbital possible in which hybridization amount? sp hybridization. Yes, in that first number always number of bond pairs and second number is always number of lone pairs. Okay, now I will tell you some charge species I will take. Just you see, for example, NH4 plus. How to apply the formula? So without formula, doing theoretically too complicated. That's why I will tell you formula. What is the central atom here? Nitrogen. Around this central atom, I want number of hybrid orbital is equals to. Around this central atom, how many atoms were there? 4 hydrogen atoms is the plus of into group number of central atom, nitrogen. Which group element? 5th group element minus. Each hydrogen can form 1 bond. 4 hydrogen can form 4 bonds. Minus 4. Yes, plus or minus charge. Okay, in the space plus is there. Write down in the formula opposite sign. It is indirectly plus 1. Can be written as here minus 1. Particle to formula opposite has to be maintained. Then what we are getting? 4 plus 5 minus 5 0. By anything 0. We want 4 hybrid orbital. 4 hybrid orbital means which hybridization we are getting? sp3 hybridization we are getting. You know very well. First number is always bond pair. Second number is always lone pairs. Okay, just I will tell you one more formula. You see carefully. For example, SO4 2 minus is there. What is the hybridization? You see, in SO4 2 minus central atom is sulfur. So number of hybrid orbital is equals to number of atoms around the central atom. How many are there? 4 oxygen atoms is there. Plus of into group number of sulfur 6 minus every oxygen can form 2 bonds. 4 oxygen can form 4 2s are 8. Bond formation capacity we are calling as valence. Minus 2 is there. How we will write in the formula? Plus 2. Plus 4. 4 plus 6 minus 8 minus 2. Minus 2 plus 2 0. Anyway, like this. We want 4 hybrid orbital. We want possibility hybridization. sp3 hybridization. Okay, now always first number is bond pair. Second number is lone pair. It's also very important question. What are the hybridization? What are the number of lone pairs and bond pairs? He will ask everything. All of you clear? So neutral space and charged space. Okay. Now we are going to discuss some important concept here. See carefully. So in hybridization, 90% is okay, but in some cases it's also failed. Hybridization concept. What is that failure of hybridization? I will tell. So failure or drawbacks. Failures of hybridization. So where it is failed and what is the minus or drawback in the hybridization concept. You take for example H2O molecule and NH3 molecule. Apply the formula. Here you are getting sp3 hybridization. Here also we are getting sp3 hybridization. Actually, according to sp3 hybridization, which shape has to be get? Tetrahedral shape has to be get. Tetrahedral shape. And bond angle should come 109 degrees, 28 degrees. But it's not like this. This H2O molecule having which shape? Angular shape. Angular shape, or also calling as V shape. Also called as bent shape. Bent shape. So what is the meaning of this one? If you take this molecule, O will be there, coming here H, here H. Is that angular shape or bent shape or V shape? After that has 2 lone pairs. Already we applied the formula. Here NH3 is there, no? This is having a pyramidal in shape. Pyramidal in shape. So what is the meaning of pyramidal? NH like this and has lone pair. It's actually both are involved in the same hybridization. Should get tetrahedral geometry, but water is having angular shape, but ammonia has a pyramidal shape. Here angle is coming around 109, 104 degrees. Here angle is coming 107 degrees. So why this variation is coming? Means hybridization didn't explain anything. So means hybrid. Why this variation is coming? Because of these lone pairs. Means hybridization concept is failed when molecules are having lone pairs on the center atom. When hybridization is failed, When the molecules are having some lone pairs on the central atom, then the bond angles and shapes is not explained by hybridization. To overcome these